I decided today that I would just use some slides because I have some slides on the exact thing that I want to talk about today, and also then the picture's going to be a lot nicer than what I'll draw on the board. So, all right. So the point of this is to try to understand what it really means for two graphs to be quantum isomorphic. This is specifically for quantum commuting isomorphism, because we have this definition, and then we have this reformulation in terms of quantum permutation matrices. But that's fairly algebraic, and maybe it doesn't give you a real sense of what it means for two graphs to be quantum isomorphic in a way that sort of tells you, okay, well, if one graph has this property, then the other graph has to have this property, something like that. And it's certainly not a very combinatorial description of the relation. But it turns out you can get a very nice combinatorial description, a rather surprising one. But to do that, you actually need to use the machinery of quantum automorphism groups of graphs, which is something that was actually defined before quantum isomorphisms. And when we define quantum isomorphism, we would Google quantum isomorphism to see if anyone had come up with quantum isomorphism before. And all you find are a bunch of papers about quantum algorithms for graph isomorphism. But if we had Googled quantum automorphism, we would have found a lot of stuff. But these quantum automorphism groups are a bit weird, at least from my perspective, because, depending on how you sort of make your definitions, the quantum automorphism of a graph is not something that actually exists as a mathematical object. Rather, there's some sort of associated algebra that exists. And in the classical case, there's like sort of a correspondence between the algebra and the group. But in the sort of quantum case, there's no group. But you say it's the sort of algebra of functions on the quantum automorphism group, the graph, even though it can't be an algebra of functions because it's not commutative. So it's quite confusing when you first start reading papers about quantum automorphism groups, because you keep trying to figure out what the definition of the quantum automorphism group is, and all you find is the definition of this algebra, and you keep trying to figure out, well, what's the actual group or quantum group or whatever it is. Okay, so the way we get this nice description is through counting homomorphisms. So we already know what homomorphisms are. We talked about that the first 3 days this week. And these are just classical homomorphisms. We don't have to count any quantum homomorphisms, luckily. But now we don't care about just about the existence, we care about the number of homomorphisms. And there's an old theorem of Lovaas that says that the homomorphism for, say, two graphs G and H, they'll be isomorphic if and only if they have the same number of homomorphisms from any given graph. Well, one direction is obvious. If they're isomorphic, obviously these numbers are going to be the same because they're really the same graph up to relabeling. But the other direction is non-trivial, though it's not a very hard proof. Although it was a significant result at the time, because he could use it to prove some other stuff. And so our result is going to be sort of analogous to this, sort of a quantum analog of this. And what we proved is that two graphs are quantum isomorphic if and only if they have the same number of homomorphisms from any planar graph. And I think it's rather surprising. I mean, certainly we were surprised when we figured it out, because when you see this definition of quantum isomorphism, I mean, nothing about it is screaming homomorphism counts or counting anything or planar graphs. Of course, going through the proof, you start to see some sort of reason for the connection to planar graphs and homomorphism counts, but it's still, I think, rather a surprising connection. I don't think I mentioned this, maybe Laura mentioned it, but actually it's known that quantum isomorphism is undecidable. And this means that this sort of combinatorial problem of, if you're given two graphs G and H, can you find, or can you determine even if there is some planar graph that has a different number of homomorphisms to those two graphs? That's an undecidable problem. Maybe that's not surprising, because you think, well, I have to check an infinite number of, I can have to check all the planar graphs. There's an infinite number of them, right? But of course, if I replace planar graph, which is any graph, right, then the problem is equivalent to isomorphism, which is at worst quasi-polynomial time. And there are other families with the same problem as polynomial. Okay, so I'm going to find this type of relation on graphs, this congruence sub f, where f is some family of graphs, and it just means that the number of homomorphisms to G and H is the same for all graphs in that family. And it turns out there are sort of several results about such relations. Of course, we already talked about Logos's result. Probably lots of people in here are familiar with co-spectrality, right? This is for adjacency matrices. This is the same as having the same number of homomorphisms from any cycle. This is usually phrased as having the same number of closed walks of any given length, right? Because this tells you the traces of the powers of the adjacency matrix. And from that, you can determine the eigenvalues. If you count from cycles and paths, then you get the relation of being co-spectral with co-spectral complements. These are kind of folklore. Well, this one is folklore. I actually don't know if I've seen this anywhere, but this is true. So more recent result is if you count homomorphisms from trees, which is certainly a natural class to consider, you get what is known as fractional isomorphism, which Laura spoke about on Wednesday. Right, this is this linear relaxation of isomorphism, where instead of asking for a permutation matrix P such that A sub G times P equals P times A sub H, I relax it to only needing a doubly stochastic matrix. And it also has very, very many reformulations that are combinatorial or based on logic or something like this. And this is also generalized to counting graphs of tree width at most K. And this is equivalent to the two graphs in question being not distinguished by the k-dimensional Weissteiner alignment method. And this is some sort of like graph isomorphism heuristic where you kind of are doing something about looking at k-tuples of vertices in the graph, and you're kind of labeling them in a certain way, and then you kind of refine this labeling over and over again until it stabilizes. Even more recently, Martin Grohe has characterized homomorphism counts from tree depth in most K graphs, and this is in terms of some first order logic, something I don't really know much about, but there's a characterization. And of course, our result is for planar graphs, we get quantum isomorphism. I should say quantum commuting isomorphism. And I should also mention that there are some natural, well, I would say natural families where they're not all graphs, but you get isomorphism back somehow. So you don't necessarily have to count homomorphisms from all graphs. So if we take two degenerate graphs, so these are graphs that such that any subgraph has some vertex of degree at most 2, then if you count homomorphisms from these, then this is equivalent to isomorphism. That's by Dvorak. Okay, I think maybe Laura mentioned these two graphs. So these are not quantum isomorphic, these two graphs, this Rook graph and the Shrikhanda graph. But originally it's sort of was non-trivial to prove that they're not quantum isomorphic, because essentially the best necessary condition we had before was that they're not distinguished by two-dimensional Weissteiner layman. And these are strongly regular graphs with the same parameters. And so they are not distinguished by two-dimensional Weissteiner layman. So that necessary condition is fulfilled, right? So, but that doesn't mean that they're quantum isomorphic, right? And we had to use some sort of a quantum parameter. Like if you take the quantum correct number of the complements, it's different. But this was essentially just a kind of brute force approach. But now, well, the Rook graph has K4s. The Shrikhanda graph does not have K4s. So they have a different number of homomorphisms from K4, which is planar. So you're done. Okay, this is more kind of like a joke application, but I think it's cute anyways. So these are our two quantum isomorphic graphs that Laura showed you on Wednesday, and that I also mentioned about the construction yesterday. Now the graph G, it's actually homomorphically equivalent to K4, meaning it's four colorable and it contains a four clique. And so that means that some given graph F has a homomorphism to G if and only if it has a four coloring. On the other hand, a planar graph has a homomorphism to G if and only if it has a homomorphism to H by our theorem. Right? So what that means is, okay, so what that means is that in order to prove that a planar graph has a four coloring, it's sufficient to show that it has a homomorphism to H. Because then it has a homomorphism to G, which has a homomorphism to K4, so it has four coloring. Okay, but somehow this graph H in general, it's easier to have a homomorphism to H than to be four colorable. Okay, because this graph H is chromatic number 5 actually. So for instance, H is a homomorphism to itself, but it's not four colorable. Right? So in principle, we have made it easier to prove the full color theorem. Of course, this is ridiculous because no one is going to prove that every planar graph has a homomorphism to this 24 vertex graph. That's silly. But I always thought it was kind of funny and interesting. Okay, so the way we prove this this combinatorial description of quantum isomorphism is using the technology of quantum automorphism groups of graphs. Let's start with classical automorphisms. I think we all know what these are, right? We already know what an isomorphism is, and of course, an automorphism is just an isomorphism from a graph to itself. The difference here is now they form a group under composition, of course, right? Called the automorphism group of the graph. And you can also think of these as permutation matrices. They're exactly the permutation matrices that commute with the adjacency matrix of your graph. All right. So what exactly is a quantum group? And as I said, it's a bit of a strange thing. But the general idea is that if I have, say, a compact group, I can look at the algebra of functions from that group, sorry, algebra of continuous functions from that group to the complex numbers. And this gives me a commutative C-star algebra. And it has some extra properties such that any commutative C-star algebra with these properties actually comes from being the algebra of continuous functions on a compact group. So this is kind of one-to-one correspondence. Right? But then you could consider the same types of C-star algebras with these same properties, but drop the commutativity requirement. And now we just say, oh, these are the algebra of functions on some quantum group, even though they're not the algebra of functions on anything, because if you're an algebra of functions, you have to be commutative because your multiplication is some like just pointwise multiplication. Okay, but that's sort of the general idea. And that's kind of, I guess, the intuition. Okay, but let's get a little more specific. Let's look at the quantum automorphism group of a graph. Again, the thing you're actually going to be defining is an algebra, a C-star algebra. Okay, and we use this notation C of some quantum group. This means the algebra of functions on that quantum group. Okay, and this is a universal C-star algebra generated by some elements Pij. So I'm not going to go into detail about what exactly that means, but for intuition's sake, this is kind of like defining a group in terms of generators and relations. Right, so generators, I say they should satisfy some relations, and I take kind of like the most general C-star algebra satisfying those relations. Okay, what are the relations that these Pij need to satisfy? Well, the first is that they're all projections. Okay, and the second is that if I sum over one of the indices, I get identity. Okay, of course, we know that this is the same thing as saying that if I make a matrix out of these Pijs, I get a quantum permutation matrix. Okay, and then the last condition is just saying that I want this quantum permutation matrix to commute with my adjacency matrix. Okay, so this is kind of analogous to the classical case of the automorphism group. Now, if I were to add the extra relation that I want all of the Pij to commute, then what I would get is kind of an abstract way of defining the actual algebra of functions on the classical automorphism group of the graph. And the correspondence there is that this Pij element would correspond to the function that takes an automorphism of your graph to the ij entry of its permutation matrix representation. Okay, another way to think of it is this is the characteristic function of automorphisms that map I to j, or j to I, depending on how you want to do your multiplication. Okay, and we call this matrix P the fundamental representation of the quantum automorphism group of the graph. All right, so that's quantum automorphism group. Any questions about this? I know it's a bit strange, right? Maybe unfamiliar to some people, but this is just some, some algebra, has some generators, satisfies some relations, and we don't really need to know a lot of deep stuff about this.
I have a question. So can we just think of it as a terms of collection of quantum permutation matrices, where each entry is just a projection over R or C?
You can't think of it as a collection of quantum permutation matrices. It's really just an algebra generated by the entries of actually a specific quantum permutation matrix, right? So I mean, it really is an algebra. It's not a collection of matrices.
Okay. So if you prove that every quantum permutation with say real or complex projections satisfy something, does it follow that the algebra satisfy that?
Yeah. Like for instance, if you show some sort of relation that maybe is implied by these relations, right?
Then
Any quantum permutation matrix that that satisfies this, it will also satisfy that relation.
But we don't have the other way around.
If you want to show that every single quantum permutation matrix that satisfies this
Yes.
has a certain relation, then yes, then of course this is a specific quantum permutation matrix that satisfies this, so it will also satisfy that relation. I mean, this is defining an algebra abstractly, but it is defining an actual concrete algebra. Just like when you define a group using these generation relations, it is an actual concrete specific.
That bold one in the middle, is that just the identity element of the algebra?
Yeah. I think I've been using I in the previous talks, but
Okay, yeah.
okay. And maybe I should also point out for some graphs G, even though we don't explicitly require this commutation relation, it can be implied. For instance, if you take some complete graph on 3 vertices, that's even though you don't require this commutation explicitly, it actually will be commutative. If you take any cycle other than the 4 cycle, then it will be commutative. And of course, there are many other families known, but those are some simple ones. So let's consider this fundamental representation of our quantum homomorphism group. And we're going to define a relation on the vertices of our graph. We say that I is sort of 1 related to J if this Pij is not just the 0 element of our algebra. So it turns out that this relation is an equivalence relation. And in the classical case, well, what does this mean? The classical case would mean that there's some automorphism that maps I to J, meaning that I and J are in the same orbit of the automorphism group. Right? So then we just take this to be a definition of orbits of the quantum automorphism group, the equivalence classes of this relation. Okay, and then we get this nice theorem which allows us to kind of completely reformulate the notion of quantum isomorphism in terms of quantum automorphism groups of graphs. And it's exactly analogous to the classical statement. It says that if I take 2 connected graphs G and H, then they're going to be quantum isomorphic if and only if, when I take their disjoint union and I look at the quantum automorphism group of that disjoint union, there's one vertex from G and 1 vertex from H that are in the same orbit. And so classically, this would mean that there's some automorphism that maps my vertex from G to this vertex from H. But of course, since the graphs are connected, it would actually mean that I have to swap both the 2 components in the disjoint union, and that would give me an isomorphism from G to H. And this restricting to connected, this is not really a restriction at all because, well, by taking complements, I can always assume G is connected. Right? Taking complements, that preserves quantum isomorphism. So I can assume G is connected, but you can also show that a connected graph can only be quantum isomorphic to a connected graph. So this is really sort of completely characterized as quantum isomorphism. Okay, so here we define this notion of orbits, and here we can sort of reformulate quantum isomorphism in terms of these orbits. So what we want to do is kind of, to get our combinatorial reformulation of quantum isomorphism, we want to have some sort of combinatorial understanding of these orbits of the quantum automorphism group. And to do that, we are actually going to look at something that is a more general thing than orbit. These are called intertwiners of the quantum automorphism group, and these are just some complex matrices. Okay, so again, we take this fundamental representation of our quantum group, and we consider this these tensor powers of this fundamental representation, where this is just going to be a matrix where the entries are indexed by k tuples, like the rows and the columns are indexed by k tuples of vertices from our graph G. Okay. And if I look at the sort of I1 up to ik, comma J1 up to jk entry, I just take pi1 j1 times pi2 j2 dot 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 times pik jk. It's sort of, I mean, it's the same sort of notion as the usual tensor product, but now the entries are elements of some algebra. This here is product, not tensor product. Okay, and then we can define an LK intertwiner of the quantum automorphism group. It's just a matrix, and it's not like a matrix with algebraic with entries from some algebra. It's just a matrix with complex entries that satisfies this kind of intertwining relation. By multiplying the left by p to the tensor L, it's the same as multiplying on the right times p to the tensor k. So it's kind of like a commutation relation, but the k and L don't have to be the same. And this is just some notation. This is sort of the set of all intertwiners. It's just denoted by the C sub q to the G. And I should point out that I don't know if it's on the slides. No, it's not. Okay. So classically, what are these intertwiners? Well, they're exactly the matrices that are constant on the orbits of the automorphism group on L plus K tuples. Right. So I mean, if I think, this is indexed by the rows here are indexed by an L tuple and the columns by a K tuple. Right, so each entry I can think of as sort of being corresponding to some L plus K tuple. And this relation in the classical case says that this matrix T is constant on the orbits of the automorphism group on L plus K tuples. Okay, so this is just kind of, in the classical case, just some kind of algebraic encoding of the orbits on higher, like on tuples of vertices in your graph. Which of course completely determines the automorphism group, right? Because if I know the orbits on, say, number of vertices tuples, right, then that tells me all of the automorphisms. But in this case, there's no longer this correspondence between, at least for higher values of L and K, this no longer this notion of orbit on L plus K tuples for the quantum automorphism group. Okay. For one tuples, yes, we define the orbits there, and even for two tuples, you can do it. But for higher order, you can't. Okay, and this set of intertwiners, it's closed under various operations, and this is sort of just follows from the definition. So, for instance, matrix product, of course, matrix product where you can take the actual product, right? Not all of these are the same size matrices. Okay, tensor product, conjugate transpose, and linear combinations. Again, linear combinations of things of the same size. And I mentioned this briefly just now, like a 1,0 intertwiner. Okay, this is exactly something which is constant on the orbits of the quantum automorphism group.
I think you just told us that in the classical case, this thing is also closed under entry-wise product.
That's true.
But in the quantum case, you don't have that?
No, only for L plus K less than or equal to 2.
Okay, thanks.
Also, another question. What is P to the tensor power 0?
Yeah, that's like a 1-by-1 matrix with the identity element in it.
Okay.
That's a good question. Okay, yeah, so 1,0 intertwiner, these are just the things that are constant on the orbits of the quantum automorphism group, or you can think of it, it's the span of the characteristic vectors of the orbits. I'll just briefly mention, I don't think I have it in these slides. If I look at the 1,1 intertwiners, right, so this corresponds to matrices that are constant on orbits on two tuples, which you can define similarly to orbits on just vertices, and this will form a coherent algebra. So you can get this notion of of course, there's a corresponding coherent configuration, but we just need the orbits. Okay, so let's look at some examples. Well, by definition of the quantum automorphism group, the adjacency matrix is a 1,1 intertwiner. Right? That's just part of the way we define the group, the quantum group. There's another intertwiner. This is usually denoted M. Sometimes it's called the multiplication map, and it acts on sort of a 2 tensor, and it just takes EI tensor EJ to either a single copy of EI if I and J were the same, or maps it to Z. Okay, and the adjoint just takes a single copy of EI and gives you 2 copies of E sub I. And then the all ones vector is also a 1,0 intertwiner. And maybe I'll point out these second two, M and U, these exactly correspond to this matrix P being a quantum permutation matrix. I just, okay, I didn't realize that's what it said. Yeah, so this is exactly characterizing this quantum permutation matrix property. Okay, and there's a theorem by Chassinol that says actually for the quantum automorphism group, these 3 intertwiners are all that you need. Okay, everything else is generated by these 3 intertwiners, and use this to denote linear combinations, matrix product, tensor product, and conjugate transpose. You also have that for the intertwiners. This is the intertwiners for the classical automorphism group. If I remove the Q, they're generated by those 3 plus 1 more, which is known as the swap map. Right? It takes EI tensor EJ to EJ tensor EI, and this exactly corresponds to these entries in your quantum permutation matrix community. So this extra thing corresponds to commutation, which is why you have it for the classical one, but not the quantum one.
So what do they form as a generated by all those relations? It's not an algebra. This is not.
It's not an algebra. I mean, there's something called tensor category with duals. That's what they form.
Oh,
Okay. Okay. And I should also point out that somehow like these intertwiners, they somehow characterize this quantum group in the same way that in the classical case they would characterize the automorphism group. Okay, we need some. Okay, but what we want to do here is we want to find a combinatorial description of these intertwiners, and the way we're going to do that is we're going to try to understand these three generators combinatorially, and then we're going to understand, or not linear combinations, but these three operations combinatorially. Okay, and the way we do this is with something called bilateral graphs. And I think these are, Bill last week spoke about something called scaffolds. I think these are probably almost the same thing, or maybe even exactly the same thing. I wasn't here last week though, so I'm not responsible for knowing that. Okay. What's the bilateral graph? Well, it's actually very simple. It's just the triple, where the first thing is a graph, and then the next two things are tuples of vertices from that graph. All right, and if it's an L tuple and a K tuple, we say it's an LK bilabeled graph. Okay, here's a simple example. In this case, the graph is the complete graph on 4 vertices. Let's say that the vertices are 1, 2, 3, 4, and then the first tuple is 1, 2, second tuple is 2, 2. Not very interesting, but we want to be able to sort of picture these in our head, or we want to be able to draw them, right? Just the same way with graphs, we don't think of them as a set of vertices and a set of edges. We think of them as some picture, usually, I think. Okay, and so we want to do the same thing here. Well, we know how to draw the graph, but we need to add something to the picture to sort of encode these tuples. Oops. Okay, and the way that we do this is we add what we call wires. Okay, for the first tuple, it's 1, 2. So we're going to have a wire coming off of 1 going to the left, and a wire coming off of vertex 2 and going to the left. And the order is indicated by sort of the wire corresponding to the first entry of the tuple. When it gets to the left side of the diagram, it should be the first one starting from the top. And similarly, the wire that goes to 2, which is the second thing in the tuple, should be the second wire over here. So if it had been 2, 1 instead of 1, 2, then this wire should go up here, and this wire should go down here. And then for the second tuple, the wires go to the right. And you can have repeats in the tuples. There's no restriction. Okay, here are some very suggestively named bilateral graphs. Okay, so this is just the graph with a single vertex and no edges, and then 1 wire to the left. This is a single vertex, no edges, 1 wire to the left, 2 to the right. This is a K2, so 2 vertices with an edge between them. 1 vertex has an edge going to the right, a wire going to the right, and a wire going to the left. And then here you have 2 vertices with no edges, and then on the left-hand side, the wires, each one has 1 wire, and on the right-hand side, each one has 1 wire, but in the opposite order. Okay, so I want to use these to describe these intertwiners, and in order to do that, I need to somehow get some matrices out of these bilateral graphs. And the way we do that are with what we call homomorphism matrices. Okay, so we fix some graph G, and we consider a bilateral graph F. Then the G homomorphism matrix of F, it's going to have entries that are indexed. The rows are indexed by L tuples of vertices from G, and the columns by K tuples of vertices from G. Okay, and we denote it by this T to the F arrow G. And the way, so this entry in this homomorphism matrix, it's just going to be the number of homomorphisms from F to G that map A sub J to U sub J. Or this A sub J, that's from this tuple in the bilateral graph. And then it maps B sub I to V sub I. Okay, so essentially what you're doing in this homomorphism matrix, you're counting all of the homomorphisms from F to G, but they're being partitioned according to the images of these A sub J's and these B sub I's. So let's look at a simple example. Let's take this bilateral graph A. So if I look at the UV entry, well, that's the number of homomorphisms from this K2 to G that maps 1 to U and maps 2 to V. Okay, but if I map 1 to U and 2 to V, that completely determines the map, right? And it's either a homomorphism or it's not. And If it is a homomorphism, there's exactly one. And if it's not, then there's 0. Right? And it's a homomorphism exactly when U and V are adjacent. So I get 1 when they're adjacent, and I get 0 otherwise. Of course, we all know what this matrix is. It's the adjacency matrix of our graph. Okay, and you can similarly show that these other bilabel graphs with the sort of suggestive names, they correspond to the intertwiners with the same name, but without the arrow. Now we sort of have a combinatorial understanding of A sub G and U and M, and they're the things that generate our intertwiners. And so now we just need to understand these operations. So we sort of know now that what we want is to understand these operations. Okay, so let's look at the first one is matrix multiplication, or we call it composition. And what you do is you take 2 bilabel graphs, but they can't be arbitrary. They need to sort of match dimension. So one needs to be an LK bilabel graph, and the next one needs to be a KR bilabel graph, for instance. Same with matrix multiplication, right? Okay. And the way that you take their product or their composition is you draw F1 here, you draw F2 to the right of it. Now, this sort of dimension matching means that the number of wires here is the same as the number of wires here. And what you do is you just join up the first wire here with the first wire here, and so on. And then you contract all those wires. Okay, you keep the wires over here and the wires over here, and you get some new bilabel graph. And that's the product. Okay, this is something that's maybe a bit more concrete. This is kind of an abstract picture, right? And so you can see, for instance, I end up getting a loop here because this vertex 3 has a wire going here, which makes it merge with C, but it also has a wire going up here, which makes it merge with A. But so then that means all A, 3, and C get merged, but there's an edge between A and C, and that edge becomes a loop. You can also I mean, it might be the case that you get some multiple edges this way, but actually multiple edges would just replace with a single edge, because when you're counting homomorphisms to graphs that have no multiple edges, you can just ignore them. Okay, but we need to keep the loops, right? Because even if we're only counting homomorphisms to graphs that have no loops, when we get a loop, it would mean that we now have 0 homomorphisms, right? And if we ignore it, then we won't have 0 homomorphisms necessarily. Okay, so that's how you define this product. And of course, the theorem is that this combinatorial notion of product exactly corresponds to this matrix multiplication. If we take the product of 2 of these homomorphism matrices, it's the same as taking the homomorphism matrix of the product of the bilabel graphs. Okay, and then we can also do the same for tensor product and transpose. Tensor product, actually, the composition is sort of the most complicated one. Tensor product is easy. Actually, all you do is you take disjoint union of the 2 graphs, and then you concatenate the tuples. Okay, so graphically, it's just taking your F1 and then drawing F2 underneath it. Okay, and again, you have the theorem that the bilabel graph operation corresponds to the matrix operation. And then this conjugate transpose, or this star operation, all it does is it swaps the left and the right tuples. Okay, and that corresponds to just reflecting your picture about the vertical axis. Okay, so now we understand how these generators, we understand sort of a combinatorial way of describing these generators, and we know how to describe these operations combinatorially. So now the question is down to, well, what are the bilabel graphs generated by these 3 bilabel graphs and these 3 operations? Okay, and it turns out that what you get are essentially something known as a planar bilabel graphs. To define this, we need to define this auxiliary graph, F circ. So I take some bilabel graph, and to define this F circ, essentially what I just do is I just draw a circle around this picture that touches the ends of these wires, right? And then I make the place where the wires touch the circle into vertices, and then I change the wires to edges. Okay, and so that's what I've done here. Okay, so now this is just a graph, and we call this cycle that we added the enveloping cycle. Okay, and then this class of planar bilabel graphs, these are just the graphs, the bilabel graphs F, such that this F circ has a planar embedding where this enveloping cycle bounds the outer face. It doesn't have to be the outer face or any face, it's the same, but we might as well draw it with it bounding the outer face. And equivalently, we could add an extra vertex here that's adjacent to all of the vertices on the cycle, and then that's equivalent. This is equivalent to just that new graph being planar. Sometimes that's easier to use. Okay, and then the theorem is that these are exactly the graphs that are generated by these three bilevel graphs and those operations. So here's sort of the very quick run through of the proof, just sort of pictorially. I need to. The first thing is we need to show that the planar bilevel graphs are closed under these three operations, right? So that will prove this first containment, because we certainly those generators are among the planar bilevel graphs, and if the planar bilevel graphs are closed under these operations, then this set generated by those operations will be contained in it. Okay, so let's take two. We're just going to do the composition. Let's take two planar bilevel graphs, and we draw their f-circ next to each other. And then now we're just going to add some edges between certain vertices on this enveloping cycle, and we actually add an extra vertex sort of between like the first vertex to the left and the first vertex on the right on that enveloping cycle, and similarly on the bottom. All I did now is I removed some edges. Okay, I removed some edges from the enveloping cycle. Okay, and now I have something where I have these passive link 3, and of course these are essentially like these wires that I join up in this composition operation. And so I contract those passive link 3. I'm left with essentially, this is essentially what I want, but I am left over with these extra vertices just for some technical reasons. And then I just unsubdivide to get rid of those. Okay? And sort of everything sort of, hopefully you can see that everything kind of remains planar when we're doing these things. Of course, that's not a proof, but it's not so hard to convince yourself, I think, that that's what happens. And then we end up with the f-circ for the product of f1 and f2. And we can see that this is still a planar graph where this bounds the other face. Okay, so that's one direction. Now we need to show that every planar bilevel graph can be created using these three bilevel graphs and these operations. This is a little bit trickier. The idea is you want to sort of pick some vertex from your planar bilevel graph that you can sort of carefully kind of pluck out so that you're left with some smaller planar bilevel graph that you can then compose with some very basic, obviously planar bilevel graph, or sorry, some basic graph that's obviously in this set. And then by induction, their product will still be in that set. Okay, so we pick this vertex V. Such that all of its neighbors that are on the enveloping cycle are consecutive. And you can always find that. If you couldn't find that, then it wouldn't be a planar bilevel graph. Okay, and then we're going to contract all these edges to the enveloping cycle. And that sort of brings this vertex V out here to the cycle. I just draw a circle around V, and where I hit the edges, I make vertices, so everything stays planar. I delete V, and also this edge between W1 and W2 here. And then I just unsubdivide this W1. I just remove W1 and W2 by unsubdividing. Okay, and now I have this smaller, still planar bilevel graph. And so by induction, this is in this set on the right here. And then I can combine this. I can actually multiply this by something that essentially has a vertex, or I have a vertex like this, and then it will have however many neighbors it needs to have. So it'll be just a star graph is the underlying graph. And then you match up, you need to put some wires on the degree 1 things that go to the right. And then enough wires on the right number of wires on V that go to the left. But it's just some small thing that you compose. Okay, and that proves the other containment. Okay, so that's sort of the main part of the proof, actually. So I mean, almost in the paper, almost all the time is spent proving these two containments because sort of to do it in detail with these planar arguments, it's kind of tedious. Now that we have that, we want to show that this quantum isomorphism is equivalent to the two graphs having the same number of homomorphisms from any planar graph. So one direction is not so hard. Well, neither direction is super hard, but one direction is easier than the other. If they're quantum isomorphic, then we have this quantum permutation matrix satisfying this equation. And you will also have that because this is a quantum permutation matrix, right? if I take m times p tensor 2, it will be equal to p times m. And that's just because that's a relation that holds for any quantum permutation matrix. Remember, I said that sort of this u and m being an intertwiner, this is exactly characterizing what it means to be a quantum permutation matrix. And similarly for the relation with u. And so what that means is that for any planar bilevel graph F, if I put in this homomorphism matrix for F here, times the appropriate tensor power of P, what happens is that when it goes, I can move it through the other side. This is an expression in this UM and A sub G, right? And the U's and the M's, they stay the same when they move over here. But the A sub G, it just turns into A sub H. So I get the same expression here, but with all the A sub G's replaced with A sub H. And that, of course, corresponds to the same bilevel graph, but now it's the homomorphism matrix for H. Okay, and you can show that this correspondence, it preserves the sum of the entries. And that means that the sum of the entries of these two things are the same, but the sum of the entries is just the total number of homomorphisms from the underlying graphs. So I get that the number of homomorphisms from any planar graph is the same to G and H. Okay, so like I said, the converse is a little bit trickier because essentially now you only have access to the sum of the entries in these homomorphism matrices. Right? You only know the sum of the entries in a given homomorphism matrix for G is the same as the sum of the entries in a given homomorphism matrix from H. But you can use some kind of like simple tricks to sort of to get what you need. So first, we can assume that they're connected. That doesn't hurt anything. As I said, we only have access to the sum of the entries in a certain sense. But what we can do is we can consider entry-wise powers of 1, 0 intertwiners. Remember, Bill asked before or mentioned before that for these higher level intertwiners, it's not closed under entry-wise product, but for the 1, 0 intertwiners, it is. And so that means that for a given 1, 0 intertwiner, okay, I have that the sum of the entries for G and for H is the same, but also for all of the entry-wise powers. But from that, I can actually determine the multiset of the entries. And I know that the multiset of the entries is the same for both graphs. And then it's just another small step to go from there to see that there's some correspondence between the characteristic vectors of the orbits for the quantum monomorphism group of G and the quantum monomorphism group of H. So we have some one-to-one correspondence between these orbits. So what we do is we pick some U and G and U prime and H that are in corresponding orbits under this one-to-one correspondence. And then we consider the disjoint union, we'll just call that X. And then if we take some connected planar 1, 0 bilevel graph, we can see that when I look at the U entry for the X homomorphism matrix, it's the same as the U entry for the G homomorphism matrix. And this is because F is connected, right? So when I map it to X, it must map to just one of the components. Okay. What's a 1, 0 bilevel graph? It's just a planar 1, 0 bilevel graph. It's just a planar graph with a marked vertex, essentially. We have one wire. Like this enveloping cycle condition is essentially trivial in that case. Okay. And the same for H, right? If I look at the U prime entry, it's the same as in X and in H. So now let's consider the characteristic vector of the orbit for the quantum monomorphism group of G containing U, that's R, and similarly we take R prime for U prime. And now we look at the entry-wise product with R and this homomorphism matrix, this G homomorphism matrix for F, and the same thing. So this has to be equal, right? This is the characteristic. This is some 1, 0 intertwiner. This is the characteristic vector of an orbit. So this is constant on all the orbits, right? We mentioned that before. This is constant on all the orbits. So when I take the entry-wise product, I just get some constant times the characteristic vector of the orbit. Similarly, for the prime for the H case. So we have these two things being equal, right? But now we can look back up here and we see that this means these two things are equal. This was for arbitrary connected Connected doesn't really make a difference. It doesn't really restrict anything. So for arbitrary bilateral graphs F, and so that means that the U and the U prime entries are always the same, which is just means that they have to be in the same orbit for the quantum automorphism group of X. That's what we have. So now I have a vertex of G and a vertex of H that are in the same orbit of the quantum automorphism group with a disjoint union. And so that means by this previous theorem we saw that they're in the G and H are quantum isomorphic. Okay, so that's, yeah, I guess I have 10 more minutes, so maybe I can say something else. So, okay, I think this is a very nice, interesting result. It also kind of leads to, well, more the context. Let me go back to a few slides, well, a lot of slides, to this where we had these different relations in terms of homomorphism counting. So if we look at this this table, what you see is that almost all of these classes of graphs are closed under minors. Okay, this is trees aren't closed under minors because I can get bars. Okay, if you take the disjoint, if you close all these under disjoint unions, okay, then they are all closed under minors except for cycles. Okay, and by the way, that's sort of why this relation is not closed under taking complements. All the rest are. Because if you have a family that's closed under minors, then the corresponding relation will be closed under taking complements. Okay, so it seems like maybe there's something nice happening for some minor closed classes. This is not a whole lot of evidence for that. Also, I mentioned these two degenerate graphs, right? They also give you isomorphism, but the two degenerate graphs, they're not closed under minors, right? So maybe, and this is a long shot, but maybe what's happening is if I take an arbitrary minor closed class, sorry, if I take two arbitrary minor closed classes, maybe I always get distinct relations. I have to be more careful than that because if I close the family under disjoint unions, it doesn't change the relation I get because the number of homomorphisms from a disjoint union is just the product of the number of homomorphisms from the connected components, right? So maybe it's if I take two classes that are closed under disjoint unions and minors, they always give me two distinct relations. And I don't know if that's true or not, but I think it's an interesting question. And what you can show is that it's equivalent to showing that for all connected graphs G, there exist two graphs G0 and G1 such that the number of homomorphisms, the number of homomorphisms from G to G0 is not equal to the number of homomorphisms from G to G1, but the number of homomorphisms from F to G0 is equal to the number of homomorphisms from F to G1 for all graphs F not containing G as a minor, right? So in order to show that every disjoint union closed, every disjoint union in a minor closed class gives a distinct one of these relations, it's equivalent to show that for any connected graph G, I can find G0, G1, so that they have different number of homomorphisms from G0 from G, but any graph that doesn't have G as a minor will have the same number of homomorphisms to the two graphs. And maybe this is sort of a little bit more concrete than the original formulation. So yeah, I just think this is an interesting question. So that's why I wanted to add it on to the end of this talk, even though it has nothing to do, strictly speaking, with quantum morphisms. Okay, that's it.
Thank you very much.
So the quantum automorphism group of the complete graphs, has that been worked out explicitly?
Well, it's hard to say what it means to be worked out explicitly, I think. Lots is known, but there's still stuff that's not known about him, I would say. I mean, for 1, 2, and 3, it's just it's commutative, so it's just the same as the classical automorphism group. But for 4 and higher, it's not commutative. That's known. But for instance, there's this question. So it's in this case, it's known as the quantum symmetric group. Okay. And there's this question in the quantum group theory: is there some quantum group strictly between the symmetric group and the quantum symmetric group? And for instance, I think it's known that the answer is no up to 5, and then it's open. So I think, I mean, yeah, I don't know. I don't really know how to answer. I know stuff is known about it. Lots of stuff is known about those, but not everything is known about them. Right. And it's not like they can say, oh, it's this algebra.
Can we write down a presentation by generators and relations?
Well, sure, the one that defines it.
Right, but that brought in quantum permutation matrices.
Sure, but this is just defined by some set of relations, right?
But what about the hypercubes?
Hypercubes, they know what the quantum automorphism group is, meaning it has some name, and they said it's this one. What does it mean to know what the group of something is, right? I mean, like, well, you have to know the group table, you have to be able to write it down. I mean, whenever I think about those questions, I start to think, what does it really mean to know what the group of the automorphism group of something is? I don't really know if I know what the answer is, right? You sort of like, oh, it's this group. Okay, we know the answer then, but do you? Sorry, I know that's a very frustrating answer. I don't have a better one.
So when you count homomorphisms from these bilabeled graphs, all the edges just go to edges. I mean, is there easy adjustment for the edges to go to non-edges or to polynomials in the adjacency or to other relations? Is there a way to color the edges in the bilabeled graphs?
I mean, I think if you want to add colors to the situation, that's fine. And you say, okay, now I have a red edge, it has to be mapped to a red edge in my graph. I think that works out fine. I mean, like if you have an edge, it has to go to some edge. It can't go to a non-edge. So I don't know.
Then you could take linear combinations
Of course, you can take linear combinations. I mean, yeah. And then, I mean, you're taking linear combinations to the corresponding matrices. I don't know a way of thinking about what is an actual homomorphism from a linear combination of things to some graph. Maybe there's a nice way of thinking about it. I just think of it as some linear combination of the corresponding matrices.
Another question. So for all of those operations that you did with graphs and wires, could you, when Bill had his course, he said that all be done with matrices, right? So can this also be done in terms of matrices only, without pictures, nice pictures?
Without pictures?
Yeah.
In what sense do you mean? I mean, you need to, like, if you want to prove this theorem about planar graphs, counting homomorphisms from planar graphs, I mean, you need, if you want, yeah, I don't know how you would do it. Okay, I mean, I guess if you want to do it without pictures, I mean, you still need to somehow use graphs, I think, because you need to say that this is counting homomorphisms from these graphs. I mean, you can write down a graph without writing that, drawing any pictures if you want. I don't recommend it. And then I guess you would have just lots of arguments. Well, yeah, I don't know what it means exactly, right? Because you need to show something's not planar, right? So if you consider that, I mean, you could take all the pictures out of our paper and it would make it just harder to read, but still correct, right? Yeah, I think it's. I'm not exactly sure how to answer that, I guess.
Yeah, but those wires corresponded to some matrices, right? So different.
The wires are indicating the vertices in the tuples, right? I mean, I guess you can think of them as like, I mean, this is some sort of like matrix living in some sort of tensor space, right? And each one of those wires corresponds to one of those tensors, right? Yeah.
Any more questions? Hey, no. Thank you very much for the course. We all enjoyed it. So let's thank David again.